Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of ramen ratings, and we're going to try to predict if a ramen is in the top 10, was ever rated in the top 10. So we can't actually see the preview here, so I'm just going to the notebook. And here I have given data about ramen ratings. Let's try to predict whether a given ramen will be a top 10 ramen or not. And we will use a multi-input TensorFlow artificial neural network to make our predictions. So let me just start by reading in the data. You can see I've already imported the imports for today. Before I go through those, let me just read in the data using pandas.readcsv. And we can grab the CSV file over here, paste it in, and take a look. Alright, so as you can see, we have each ramen has a brand, a variety, a style, a country, a number of stars, and a top 10 column. So there's only a few in here that have been rated top 10, and we're going to try to construct a model that can predict whether a given ramen will be top 10 or not. And so for this, I'm going to use NumPy and Pandas, of course, Plotly Express for visualization. For pre-processing, I really should combine these together. These are our pre-processing libraries. Regular expressions. From the Natural Language Toolkit, we're getting the Porter stemmer. Both pad sequences and Tokenizer from Keras. The standard scalar and train test split function from sklearn, and the class weight also from sklearn. And we'll use TensorFlow to construct our model. So let's see, what should we do here? How should we start this? Let's get some preliminary information on the dataset. So at a glance, we can see that all the columns except review number are objects, which is slightly surprising to me, because stars should be numeric, but it says stars is an object. In any case, we'll come back to that. We also notice that it looks like there's two missing values from the style column. Additionally, only 41 of the top 10 ratings are non-null. So let's start pre-processing with this information. Let's deal with these null values first. So I want to check which values are null, so I can use the isNA function to get that, and we'll have a true wherever it's null. So I'll sum across columns, across rows, so that we get the number of null values in each column. And like I said, there's 2 in style, and then we have a whole bunch in top 10, but that's okay because we are only interested in actually knowing if it was rated top 10 or not. So we can convert all these null values into a given value. So let's look at what kind of values are in top 10. Top 10. So data sub top 10.unique will give us the unique values in the column. And as you can see, we have a bunch of different, I would say, ratings when they were rated in the top 10 and what year. So like where they were rated and when they were rated. And we also have this, which is not a rating. So why don't we apply a little? Why don't we make a little lambda function here? So I'm gonna let's take the column top 10 and apply a lambda function that takes in some x, which would be one of these, either a null value. So one of these, right? It's going to either be a null value or one of these values. And I'm going to say we're going to turn it into 1. Actually, we'll turn it into 0 if the string representation of it is NaN. And otherwise, it'll be a 1. Make sense? So if I look at what that looks like, and I want to sum across it, we get the total number of ratings is going to be 41. Okay, so we only have 41 out of the 2,500 original rows that are actually rated top 10. So this will be a very skewed class distribution. We'll have to keep that in mind. So what I can do is, let's see. There is one more thing. There's this thing. I want to make sure I'm not encoding this as a 1. So what we'll do is data sub top 10 dot replace. We're going to replace \n with a null value. And that, yeah, so data sub top 10 is going to be equal to that. So we're just replacing this with a null value. If we look at the uniques now, we'll see that's no longer in there. And right, so we're looking for this NaN value. If we run this and then we sum, we should see it should be now. It looks like there were a few of them with \n. So we have 37 now. Okay, so this is going to be our, we're not going to, we'll make a new column called is top 10. Now if we look at data, you can see we have this new one that's is top 10. It's going to be 0 if it is not a top 10, and 1 if it is. So essentially, if it has any of these values that is not NaN, it will be a 1, and otherwise it will be 0. Alright, so with that, let's see. Okay. So let's continue let's look at the null values again. Oh right, so now we don't need the top 10 column anymore. So data.drop top 10, because now we have is top 10, which is much more useful for our purposes. And we're dropping it from axis 1. And now you can see we only have 2 missing values in the rest of the data. And we could fill this in with something, but since it's only 2, I think it's okay to drop these examples. We have still 2,500 examples. It's okay if we drop 2 of them. So what I'll do is data.dropNa, axis 0, which means let's drop any rows that have any values. And whenever we drop rows, we want to reset the index after, usually at least. And drop true ensures that we don't keep the old indices as a new column. So that's our new data. We'll look at it. How about I just put these together? Alright. Okay. So here's our data. We have is top 10 and the rest of the features. We also don't need review number. It's important. So why don't I drop that right here? Data.drop review number, axis 1. And I'll put it over here. So we'll just run that. Look at data. Okay, so this is our actual feature, data frame. So we have a number of features from brand, variety, style, country, and stars, and is top 10 as well. So I'm going to do something a little interesting today. I'm going to take the variety column, which is consisting of words, and I'm going to actually use the words in it as features. So what I want to do is separate this from the rest of the data so that we can process it differently. Actually, let me just, before we continue, I'm going to print something. I just want to print the total number of missing values, which will just be 0. I'm summing over the rows and then over the columns to get the total number. We have 0. So no more missing values. Alright. One more thing before we continue, before we separate the variety column. I remember over here, stars is actually an object. And I want to see why that is. So data sub stars dot as type numpy dot float. this is a quick way to check. Alright, so there's something called unrated in here. Alright, so what we'll do, because this is numeric, we'll make these we'll make anything that's unrated a missing value, and then we will fill it with the mean of the other ratings. So, well, first let's see how many we have. Data.query. So we're querying for unrated in the stars column. So stars equals unrated. Okay, it's only 3, but I don't see why we should drop them, because this is easily fixed if all we have to do is so okay, there's a few ways to do this. Let's see. We want to set these equal to missing values. So what we can do is data.replace, not data, I'll do data sub stars dot replace unrated with missing values. So I really should put this down here. We're not quite done yet. Okay. So I'm going to replace all the unrateds with missing values, and then I'm going to fill in the missing values. So fill in A with the mean of stars. And to get the mean, I'm going to have to convert it into a integer. Actually, I want to see if this works first. So data sub stars equals data, and I want to see if it works. Right, it doesn't work because these are actually still strings. Even if we replace these with numpy.nans, these are still string values. So all I have to do data.asType numpy.float.replace. Actually, no, we put that in the end. So we replace it, and then we type convert it, and then we can fill in A. Alright, so that'll work. So that's going to be our new column. And now we'll have no missing values, and we'll also have no unrateds. Everything will be filled in. Okay, we're finally done. So now let's move on to, how do I say it? Let me put this here. And then I'll say, here, why don't I at the top? Okay, data. Okay, I messed around too much here. Let's go. Engineering variety features. Okay, so what I'm going to do is take this variety column and convert it into a series of sequences, where each word in the sequence is going to be a unique integer that represents a word in the original variety name. So what I'll do is I'll construct this new data frame. It's just, well, it'll be a series actually. That's a subset of the original data frame. I'll call it Ramen names. And it's going to be a slice of the original data frame, but just the variety column. So if I want to look at that after, you can see we just have this, just the variety column. And now I'm going to apply some regular expressions to it to target. Basically what I'm going to do is I'm going to convert it, I'm going to stem it down to its, how do I explain this? Simplify it, essentially. I'm going to remove punctuation, I'm going to make it all lowercase, I'm going to process out any numbers, and I'm going to stem the words, which means take off any endings. So I'm going to create this new function. Why don't I paste it in, just for the sake of time. So it's called process name, and it's going to take in a name, which is one of these. It's going to set it to lowercase. It's going to remove anything that is not alphanumeric. So this is essentially removing punctuation. Let me just mark this down a little. Say make name lowercase, remove punctuation. Then we're going to change numerical words to number, So we're gonna, anything that's a number is going to be called number as a word, so that we'll be able to identify all numbers as the same. Then we're going to split it, make string into a list of words. Then stem each word. So this uses the Porter stemmer from the Natural Language Toolkit, and we're gonna, if you want to stem something, so ps sub stem dot stem is going. Let's say we stem the word lovely. Oh, actually, I didn't run this. This will just become love. If I want to do eating, that will become eat, and so on. It stems it down to its most simple form. So we'll stem each word, applying a map. We're mapping this lambda function to the list, so element-wise, and then turning it back into a list. And then here, we're just removing white space. So leading and trailing white space. That's what the strip function does. And so in the end, also we should note, if we have the empty string in our list, let's just remove the empty string. Remove the empty string, if it exists. Alright, so this is our function. And I'm going to apply this to our ramen names. So ramen names dot apply process name should look like this. It's going to take this and turn it into a much simpler version that the computer can understand more easily. Because the reason I do this is because let's say one ramen name has the word vegetable in it, another one has like with vegetables, so with an S at the end. If I didn't do this, vegetable and vegetables would be counted as different words, which is not good. So we're going to stem it down and process it a little bit so that we have as many overlapping words as possible. And then I'm going to call this the new ramen names. Okay. And we're going to need two more things going forward, which is how many unique words are there in all of our ramen names, and also how long is the longest name. So to get the longest name, it's not that hard. It will be the maximum of ramen names dot apply lambda x to length of x. So what that's saying is I'm going to apply this function element-wise to ramen names. So what that means, this thing will become a list of the lengths of each name, right? So the original list of words will become the length of that list. And then we're finding the max of that. So this will be the maximum length of a given name. And it's 13. So I'm going to call that max sequence length, max seq length. And let me just comment that a little. So this is getting the maximum length of a single ramen name. Alright, and then we're also going to want to get the number of unique words in our vocabulary. So let's write that. Getting the number of unique words in our list of ramen names. Alright, so I'm going to make a set called vocabulary. It's going to be an empty set. And for each name in ramen names, so for each one of these, I'm then going to iterate through the name. So for word in name, so now I'm going through one by one. I'm going to check if word not in vocabulary, then we're going to add the word to vocabulary. Alright, so if it's not already in our vocabulary, we'll just add it. And so by the end, once we're done with all this, we should have a vocabulary filled with unique words. And so if I get the length of it, that should give us the vocab length, which is what we're looking for. Alright, so now with these two values, why don't we just print them out? So I'll print them here, print results. Let me just space this a little better so we can see them side by side. And the vocab length is 1372. So there's 1372 unique words, and the longest name is 13, length 13. Okay, so the reason I went through all this trouble of getting this stuff, because now we're going to tokenize this Ramen names series using the Keras Tokenizer. So I'm going to construct the tokenizer. This I imported from tf.keras.preprocessing.text. And it takes in a number of words. So numwords, this is going to be the length of our vocabulary. This is why I got this value. And then once we construct the tokenizer with a given vocab length, we can fit it on the text using fit on texts. And we're fitting it on ramen names. Alright, then we'll generate a word index just for our purposes, which will be tokenizer.wordindex. And this is just basically a ranking of the words. So if I just do this now, and we look at Wordindex, you can see what's happened. Okay, it takes all the unique words and assigns them a unique integer, but based on frequency. And I also noticed that flavor and flavor are spelled differently here. They really should be the same thing. I wonder if we should actually combine those. It might not be a bad idea. Because they're so frequent, it's probably a good idea to combine them, to let them know it's the same thing. So what I'll do is I'll just modify this a little bit, and at the very end, after we've removed everything, let's see, okay, how should we do this? What we'll do is for I in range length of name, new name, if new name sub I equals flavor with an OUR, then new name sub I equals flavor just OR. Think that should be good. Let's see that now. If I run this again, oh, what happened? Oh, it's because I already processed it. Let me just reconstruct ramen names, then run this, and then look at the word index. And, okay. Alright, so now flavor is just 1. Alright, good. Okay, so like I said, each word is given a unique integer ranked in order of frequency. So this is the most frequent word, second most frequent word, third most frequent word, all the way down until 1371. Okay, so cool. Now, what we'll do is generate our sequences. And sequences is going to use the text to sequences method from Tokenizer. And it's basically like transforming ramen names. So we're passing ramen names, and it's going to use the fit that it found to transform it into a series of sequences. So I run that, and let's look at what sequences becomes. This is similar to our original list, except each word has now been mapped to its corresponding unique integer. For example, we remember the most common word was noodle, and that's number 1. So if we look up here, sure enough, we have noodle, right? Alright, so, fantastic. With these sequences, we're almost ready to feed it into our model, but we need to do one more thing. These are all of variable length, and TensorFlow has a hard time with variable length inputs. So what we should do is pad the sequences by adding a number of zeros, either to the beginning or the end of the sequence, so that all of the sequences are the same length. And we can do that using the pad sequences function. This is from tf.keras.preprocessing.sequence. So we pass in some sequences to pad, and a maximum length, maxlen. And this is going to be the maximum length of a given sequence. And we already have that. We got it from up here, 13. We called it max sequence length, right? Okay. So we can also specify how we want to pad. If I write padding post, it'll put zeros on the end. I think by default it puts them at the beginning. So why don't we put them on the end? Okay. So name, we'll call this name features, because these are our actual inputs to the model. Alright, so if I run that, and we look at name features, you can see it's just like this, but it has zeros on the end now. So we have padded all the sequences so that it's an actual NumPy array of a uniform dimension. Okay, so let's look at the shape of that. Actually, we'll get the shape of it in a second. What I can do is we're just dealing with this. Alright, so we have processed our name features. However, we have the other features to deal with. So let's say, getting remaining features ready. So we're going to look at our data one more time. And we can drop variety. So data equals data.drop variety, because we've constructed features from it. Access 1. And let's take a look at our data again. Okay. So it's about time we deal with these. Now, let's look at the data types. You can see that stars is now float. That's good. But the rest, I'm going to have to one-hot encode. And I know I have to one-hot encode because, well, actually, let's take a look at the style column. Okay, there are a number of values here. So the thing is, if we have more than 2 values in a given column, and there's no unique ordering, no like specific ordering between the values, one-hot encoding is our go-to method. So, alright, so let's actually make a one-hot encode function. This is going to take in a data frame, a list of columns, and a list of prefixes. And we're going to start by making a copy of our data frame. After that, we're going to iterate through each column prefix pair in zip of columns prefixes. So zip will pair up the values in columns and prefixes element-wise. So they'll go together into tuples element-wise. And we can iterate through those list of tuples using column prefix. So we can get them simultaneously. And we want to say, let's create a dummies data frame using pandas.getDummies that takes in a specific column in our data frame. And that's remember, that's iterating through our columns list. And we also want to append a prefix given by prefix. So if you don't know what this function does, I'll quickly show you. Let's say we want to use style, so I'll make this style. And this is actually modifying data. And the prefix, let's say capital S. You can see all the unique values in style, which were originally like this, have become columns with an S prefix attached. That's because we specified S. If we specified this style, you're going to see style would become the prefix. And what it does is just one-hot encode each one. So 0 originally had cup as its value, so now it has a 1 in cup, and zeros for all the others. You can see it right here, right? So with that, I'm going to create a dummies for a given column and a given prefix. And I'm going to concatenate those dummies columns onto the original data frame. So df equals pd pandas.concat the original data frame and the dummies data frame along the first axis, axis 1, so that's the column axis. This means side by side instead of on top. If we did axis 0, it would be on top of each other. df equals df.drop column. So we're removing the column from which we created the dummies. We no longer need it. And when we're done with that, we'll return the data frame. Okay, so there's our function. And what we're going to do is hot encode data with a list of columns and a list of prefixes. So the columns we want to hot encode are brand, style, and country. Brand, style, and country. Okay, let me delete that. We're also going to give it some prefixes. How about B, S, and C? So if we look at that, and then we look at data, we now have all these hot columns, and the original features at the beginning. Well, actually, it's just the source column. Then we have our labels column as well. So, what we can do now is separate the labels column. So what I'm going to do is call labels, taking a slice of the original data, but just the is top 10 column. And then what I'm going to do is construct other features. The reason I'm calling it other is because we already have name features here. So now we have the other features, which would be data.drop is top 10 axis 1. So this is saying other features will be everything except the is top 10 column from here, and labels will just be the top 10 column. So if we look at each one, labels is going to be an array of is top 10. Only a 1 will show if it was rated top 10. And other features will be everything except the is top 10 column. So we have stars and then all of our hots as well. Alright. So now let's scale other features. By scale, I mean let's use the standard scaler from sklearn to give each column mean 0 and unit variance. So we'll say other features equals scalar.fit transform other features. And I want to leave it as a data frame, so I'm going to turn it back into a data frame since the fit transform function actually returns a numpy array. And I'm going to set the columns equal to the original columns of other features. Okay, now if we look at other features, you can see it's been scaled so that each column has mean 0 and variance 1. And then we're going to do one more thing. Okay, so we want to put the two features on next to each other now. If you look at name features, it's currently a numpy array. So what I'm going to do is turn it into a list. So it will be a list of numpy arrays. And then I'm going to turn that into a series. So now it is a panda series of the sequences. And they're still all of the same length, but now it's stored in a series. And what I can do with that, so let me call that name features series. I misspelled features, hold on. Okay. It's going to be like this. And I'll call features, which will be all of our features, is going to be the concatenation of name features series and other features along axis 1. So we'll take a look at that. And now you can see we have the sequences as the first one. And actually we have a bad name here. Let me rename this. Let me say name equals name. Okay, now we should have name column. So we have our sequences as one feature, and then all the rest as scaled features. The other features are scaled. And we have 402 features in total, and 2,578 examples. So, what can we do now? Let's see. So we already have that. Hold on. Okay. Well, let's split it. Let's split it. So x train, x test, y train, y test. We're splitting with the train test split function that takes in, it's going to take in features and labels. And we're going to specify a train size as 70%, and we'll give it a random state as well. How about 34, just so that we can split the same way and reproduce the results. So this will give us a train and test set. So run that. And the reason I concatenated them like this is so that we can split them and get the features, the name features split the same way we have the rest of the data frame. Alright, so now let's model and train. Let's take a look at our features. So features.shape looks like this. And I also want to know, what does name features look like? 13. So the reason I'm doing this is I'm actually going to feed in name features and the other features separately. So right now, name features is attached like this, but we don't want to treat it as one feature. Right, this has 402 columns, but we don't want it as just one more column. We want it as actually 13 different inputs. Right, because 13 was the length of our maximum sequence. Each one of these is of length 13. So what we'll do is feed it in separately. So let's set up our model. So input layer. Okay, I'm not going to call it just inputs. I'm going to make two inputs. Name inputs and other inputs. So the name inputs is going to be an input layer, tf.keras.input, with a shape of 13, so a vector of length 13. So we're going to pass in each sequence as an input here. And then for other inputs, it's also going to be an input layer, but here the shape is going to be 401. And I'm going to set up each of these separately. We're going to input separately, and then we're going to concatenate them and spit out a result. So this is a multi-input artificial neural network. And okay, so I'm just going to name these so that we can see it more nicely later. You'll see why. Name inputs, and name equals other inputs. Alright, so let's just comment this a little. Training on name features. Here is training on other features. And so for the name features, we'll deal with that first. We're going to try embedding. And basically, so each word, currently it's an integer. Now we have to be able to pass in, well, we have to treat each word as a vector, in a vector form. So there's, one thing we could do is hot encode each word, but because our vocabulary length is 1371, we would require a vector of length 1371 to encode even a single word if we were doing hot encoding, because there'd be zeros in all the other spots and only one in the word that we want. A better way to do it is to use a dense encoding. So hot encoding is considered sparse encoding because there's so many zeros in the vector, but a dense encoding would be a smaller vector that still represents the word in some way, but every single element is filled, or at least most of them. So we can use a Keras embedding layer to do this. And what that does is it's going to take each word, each of our 1371 words, and it's going to shoot it off into a high dimensional vector space so that each one is encoded as a vector, you can think of it as pointing to a spot in high dimensional space, and that actually uses a lot less, a lot shorter of a vector. So for example, if we had embedding dimension, embedding dimension, so this is the dimension of our vector space. Let's say we had a 32-dimensional vector space. Then it will only take 32 numbers to convey where this word is going in the vector space. So we're actually we're going to use 64. I was experimenting with this model, and 64 works really well for this particular task. So we're going to use a 64-dimensional vector space. So it's going to take a vector of length 64 to represent each word. And that's a lot better than a vector of length 1371. So it's better than one hot encoding, essentially. And so you might be asking, well, how do we know where to send it in vector space? And that's actually learned in the model. And that's why we're going to have an embedding layer. So I'll call it name embedding, actually. That's going to be tf.keras.embedding. It's going to take in an input dimension, which is the size of our vocabulary, vocab length, an output dimension, which is the dimension of the vector space we want, which is embedding dimension, and an input length, which will be the maximum sequence length, or 13. Right, so actually up here I can just write max sequence length instead. But, you know, we'll keep it as 13 so we just know. Okay, so this is actually going to learn where these vectors go in 64-dimensional space. And it's going to group them in some intuitive way. So we actually don't know how it's doing it. Maybe it's putting similar ones together, but it's going to find essentially the best way to group them in 64-dimensional vector space. It's going to put them in the place of most meaning, because it's just going to keep doing it by trial and error, getting better and better, like any other weight in the network. So we're going to pass in name inputs here. So it's going to take in the name inputs and embed them in a 64-dimensional space, and the output of this will be vectors of length 64. Well, it would actually be 64 by 13, because we have 13 words in a sequence, and each word is now going to 64 dimensions. So normally we would encode this outside of the model, but because we're learning the weights for it, we're actually encoding it within the model. Now let's give this a name as well. So name embedding. Okay. When we're done, we're going to flatten it. So what we want is to take this 13 by 64 matrix of name embeddings, and we're going to flatten it so that it just becomes one long vector. So I'll call it name outputs. It's going to be tf.keras.layers.flatten. Let's give it a name. How about name flatten? Passing in name embedding here. So the sequences come into name inputs, go through into the embedding, get embedded, and then get sent to name outputs, which just flattens it. And then we have this output from the name model. Alright, now let's come on to the other features. For the other features, we're going to do a standard 2 hidden layer model, which we can call hidden. It's going to be tf.keras.layers.dense. So 64 activations, the ReLU activation function, and let's give it a name as well. Dense 1 should be good. And we're going to pass in other inputs, which is all the other features. Alright, and then we're going to just output straight from there. So other outputs, tf.keras.layers.dense, 64, activation ReLU, name dense2, and we're passing in hidden. So now we have an outputs from our name features and an outputs from our other features. So here, we're going to concatenate outputs and predict. I'll make predictions. So we're going to create this concat layer, which is tf.keras.layers.concatenate. It's going to take in some layers to concatenate. And what that means is because we flattened it, and because this is outputting 64 values, we're just going to take the name embeddings, which are now one vector, and the 64 the vector of length 64 from our other features, and we're just going to concatenate them together to make a single vector. So I'm going to concatenate name outputs and other outputs. And so now we have a single vector that we're going to send into outputs, which will just be one last dense layer to make our predictions. And we're only going to have one activation, the sigmoid activation function. Activation equals sigmoid. And this is because we're going to get a probability estimate for the positive class. Essentially, the probability that a given ramen is top 10. That's our single value. And sigmoid will return a value between 0 and 1, which will be a probability. And let's give these both names. So name here will be output layer, and up here, name will be concatenate. Okay. So constructing and plotting model. So our model is going to be tf.keras.model, and so we're going to pass in two inputs and an output. So inputs equals, we're passing in name inputs and other inputs. And outputs is going to be just our single outputs. Okay, then let's plot it with tf.keras.utils.plotModel and see what we get. And okay, this would be layers, sorry. tf.keras.layers.embedding. And dense object has no, what's the problem here? Oh, I didn't pass anything into the output, sorry. And cat is going into the output. Alright, and this is what our model looks like. So like I said, we have two inputs here. One is our name inputs, and one is our other inputs. And this is why I named each layer, so we can see it here. And then from the name inputs, we're going to embed it, flatten it, and send it to concatenate. And the other features are going to be fed through two dense layers and then sent to concatenate. And then once we concatenate them, we're going to generate a final probability estimate. So, let us compile and train the model. So, before I do this, I want to note I have to feed in the inputs separately. And currently we just have xtrain, which is a single set of inputs, right? So what I want to do is create two sets of inputs from this. How about xtrain1 and xtrain2? Xtrain1 is going to be just the name features. So what I'll do is xtrain subname name, which is just this column, .toNumPy, and what that will look like is this. And currently it's an array of arrays. And that's actually, if I look at the shape of this, it's actually a single vector of length 1804. So what I want to do is stack it. NumPy.stack is going to take all these different little arrays and stack them on top of each other so that we get one matrix. And if we look at that, it will look like this, and the shape of that will not be a single vector of 1804, but it will be an array of length 1804 and width 13. So essentially, this is going to be the original name features that we had before, but just from the train set. So we're sort of undoing creating a series out of it. We're undoing that and bringing it back to its original form. And that's going to be our name inputs, xtrain1. xtrain2, if we look at xtrain again, looks like this. We want xtrain to be everything except name. So xtrain.drop name, access 1. Alright, that should be that. Oh, and sorry, it should be capital. Alright, so xtrain1 looks like this. xtrain2 looks like this. And I want to do these for the test sets as well. So let's go ahead and just call this xtest1. And I'll go here and here. Sorry, and make it test. Alright. And looks good. So I guess we can put this above. Right here. So now we have two inputs for each model, and a single output, which will be ytrain. So, model.compile. I'm going to give it an optimizer atom. Loss will be binary cross entropy. And metrics, let's start with just two. Accuracy and tf.keras.metrics.auc. Let's give it a name, AUC. And we're also going to train the model. So let's give it a batch size, 64. Number of epochs, I'll train for 100 epochs, but I will use a callback that will let us converge so we won't overfit. So history is going to be where we store the fit history. This is model.fit. So we're fitting on multiple inputs. We're going to train it on multiple inputs. So we're going to pass in xtrain1 and xtrain2 as our inputs. And then our labels are just ytrain. Let's give it a validation split of 20%, batch size, and the epochs given by what we had. And we'll give it a callback, like I said. And this will be tf.keras.callbacks.reduce learning rate on plateau. So this will stabilize our training curve, and it will let us converge more easily. And let's just set verbose to 2. Alright, so I'll train that. And while that's going, let's plot the results. So I'm just going to make a plotly express figure, px.line, line chart, drawing values from history.history, and the values we want to plot are loss and validation loss. The labels, we'll set x to x will be epoch, and y will be loss. And so this is a graph of loss over time. Okay, and fig.show. So as you can see, this callback function has allowed us to nicely converge to something. It looks like it might be a little lower there, but this has given good results on the test set from what I was doing. All right, so let's get the results. The results is just going to be model.evaluate. So we're going to evaluate the model on xtest1 and xtest2 and ytest. And print that. Let us just grab a few more here. So what I mean is I'm just going to display it like this so we can see it nicely. So we have a high accuracy, but it looks like our AUC is not that great. And that's interesting. What that's saying is we're classifying a lot of the examples correctly, but we're not doing very well within each class. And the reason for this, let me display it up here. Why test? Or yeah, let's put it down here actually. So y test dot value counts should give us the number of the counts of each unique value in y test. And you can see we have 763 non-top 10 ramens, but only 11 top 10 ramens. And so what that means is we're going to see with the mean we can get the percentage of ramens that are top 10. It's actually 1.4% of our data is top 10. So AUC is low because we're failing to classify that particular class. So we can get a much better sense of this by using some more metrics. I'm going to include two more metrics, tf.keras.metrics.precision, name here prec, P-R-E-C, and tf.keras.metrics.recall, name here will be REC. Alright, so let's retrain our model. And we'll check on the results. And oh, sorry. Let me get the other ones in here. So our precision actually ended up being too small to measure. Oh dear. So essentially, precision is out of all the examples we predicted positive. So out of all the examples we said were top 10 ramens, how many of them were actually top 10 ramens? That's what precision is a measure of. And it's very possible we get 0 for this. This is saying out of all the ones we predicted top 10, none of them were actually top 10. And recall is saying out of all the examples that were actually top 10 ramens, how many of them did we get right? And it's very possible we got 0. It's saying that because there's only 1.4% that are actually top 10, if we get them all wrong, which is what recall of 0 is saying, we'll still get a very high accuracy, because all we have to do is say nothing is top 10, and we'll get an accuracy of 98 point something %, because we got all the other ones right. So what we want here is a model that's going to do well on this class. And so we're going to do a few things to try to get the model better at predicting the top 10 class properly. So one thing we can do is include class weights. And for this, I'm going to use sklearn.utils.classWeight, which will allow us to balance the classes in the loss function. So I'm going to calculate them. I'm going to call this class weights. It's going to be a dictionary made from the enumeration of, I might want to have done this backwards, but class weight, which is what we imported, .compute class weight. This is a function that takes in a mode of class of weighting. We're going to balance them. The unique values in our train set and the actual values themselves. And so once it computes the weight, we're going to enumerate it and then make it a dictionary so that we can feed that dictionary into TensorFlow. So let's look at what it looks like afterwards. Class weights. So this is what we get. Is the 0 class will be weighted very lightly, and the 1 class, which we know there are very few examples of, will be weighted very heavily. So this has 34, this has 0.5. So we're essentially making the loss function account for the, like, try extra hard to minimize loss on these examples, on the positive examples. And all I have to do to implement that is right here, specify in the fit function class weight equals class weights. And so this will hopefully allow us to get better results on our positive class. So let's reconstruct the model and run it. Let's look at the line, loss function again over time to see if it changed the results at all by adding these class weights. And it looks a little more jagged at first, but more or less we are converging. So let's look at the results. And alright, we have some values for precision and recall now. So that's much better than before. And so what this is saying is, out of all the positive predictions we made, so this is precision, out of all of the ramens we said were top 10, only 13% of them were actually top 10. And out of all the actual, this is recall now, out of all of the ramens that were actually top 10, we got 18% of them right. So this is at least an improvement, right? So this is better than what we had, certainly better, but there are some things I found that improved it even further. So the other thing I found that helped it is actually adding batch normalization before the embedding layer. And so what batch normalization does is it normalizes the training examples for each batch. So it does it neuron by neuron, giving it mean 0 and variance 1. And so I'm going to do it right here, right before embedding. So just for the names. So I'll call it batch norm is tf.keras.layers.batch normalization, and let's give it a name, batch norm. And we're going to pass in name inputs to here, and then instead of passing name inputs into name embedding, we'll pass the batch norm output into name embedding. So now if we look at our model, we have the input from the names. It gets batch normalized, neuron by neuron, and then sent to the embeddings, then flattened, then concatenated with the other inputs. So let's compile that and run it and see if we get any different results. So let's plot it. And okay, so we have a little more of jagged training, but it looks like we're good at the end. Let's see what we get. And you can see, wow, that actually decreased performance. It's very interesting. When I was doing it before, I actually had a smaller test class because I ended up dropping, where is it? The one we found, the unrated ones, before I just dropped them instead of filling with the mean. And what that actually turned out to be was that the unrated ones are actually top 10 ones. And my total number of, where is it? Here. My total number of top 10 ramens went down to 8. And so it became even more difficult for the model to accurately find those ramens. So this is, it's interesting that batch normalization did not work in this case, when previously it did. But let's actually try running it one more time, because, oh wait, hold on. Let me do this one first. Sometimes the randomness can play a role, because this is stochastic gradient descent, or mini batch gradient descent. Sometimes we can just converge to a bad minimum occasionally. So yeah, no, it looks like we were better without the batch normalization, so I'll take that off. Taking that off, and then passing in name inputs here again. And it looks like we might not be able to get any better results. So soon as this finishes, we'll take one more look. And weird, our precision went back down. Okay. Alright, hold on. Let's try it again with batch normalization. Let's take another look. I just want to review my thing to make sure that there's nothing else we're missing here. No, I don't think so. So this looks like it might be the best we're going to get. I tried so many things to try to make this better, and nothing was really working well. I managed to get better performance on the other model, but that one also had only 8 here. Let me see something. I'm just going to try one last thing, which is, let's see if we can actually see the problem with filling in the mean for those columns. Where is that? Somewhere over here. Yeah, the problem with filling in the mean for the unrated columns is that these are columns, sorry, not columns. Well, sorry, the examples that have unrated turn out to be top 10 ramens. And the problem is we're trying to predict something that has been imputed, especially in such a small class. So I want to see if maybe if we just drop those unrated columns, we can get better results. Because it's sort of like phony data. So instead of replacing, instead of this, we're just going to do, let's see, how did I end up doing it? Well, we'll query it. We'll take the index of the query, and then we'll drop those indices. So dot drop axis equals 0, and then reset the index after because we're dropping rows. Okay. So what I'll do is rerun it all the way through, and let's see now at the end. Let's see. Alright, wow, look at that. That actually did help. So now we only have 7. We only have 7 ramens. But we're doing much better. Much better. Our AUC and our recall went up. Because now these few are actually reliable. The stars rating, which I guess had a lot of predictive value, was not fabricated. And even though this looks like it's not doing as well as we originally had, which was 98% accurate, within the positive class, it's doing better. So what this is saying, out of all the actual top 10 ramens, we got 71% of them correct, and that's pretty good. That's very good. Now, given our precision is saying that we're also saying a lot more ramens are positive than there really are. We're making a lot of bad guesses about which are positive, but we are getting the ones that are actually positive. So that's a good place to end. I think that's pretty good performance. If you can find any way to improve the model, I'd be happy to hear about it. But that'll sum up today's video. I know it was a long one. Thank you so much for watching if you stuck around. And I guess I'll see you guys tomorrow, and have a fantastic day.